So, relative max and min can occur only if fx and xy are both 0. If either one is non-zero, you move in that direction and the function either increases or decreases. You move in the opposite direction along that line, it either decreases or increases. So you can't have a max or a min, okay? Now, you might think that that's all that's necessary, so you just set the x derivative equal to 0 and the y derivative equal to 0, and you have a point where you have a maximum or a minimum. But that's not necessarily the case, okay? I want to refer back to this, but I don't think I'm in shape to do that yet. It turns out that, okay, if you have a function, now let's just take the xy plane. Okay? And we have a point. Okay? If we move along this line, motion in the x direction causes change. Causes no change. So the function stays level up here as you move in this direction. Okay? And the same is true for the y direction. You go this way and there's no change. No change if you go this way, no change if you go this way. Whatever the surface is up here, it stays level, at least for a short time, as you move past this point out here. Okay? And the same in this direction. Does that assure that you have a relative maximum or minimum? Well, it turns out it doesn't, because it's perfectly possible for the function to have no rate of change in this direction at this point, no rate of change in this direction, but to decrease as you move from here to here, and to increase as you move from here to here. Okay? And that would be what we call a saddle point. This doesn't ensure a relative max or a relative min. Okay? fxy also has its effect. fxy tells you what happens if you move in one of these directions. It's possible to have a function whose graph does this along the y direction and does this along the x direction, which makes it look like it should just kind of be a paraboloid, right? But along this direction and this direction, it could decrease. So it could be like this and like this along these directions. And that's a little hard to visualize, but it's called a saddle point. If you're on a saddle, sitting on a saddle, you ride horses? No. No, I mean, it's fun. I never got to be a good rider, but I rode horses when I had a chance. Anyhow, you're on the saddle, and right here, the saddle is going down this way, right? Okay. On the other hand, in this direction, to hold you in, the saddle's going this way. So you got legs got to go over here, but it can't go down this way because you just fall off, right? The saddle has to hold you in, so the saddle has to slope in this direction. Okay? Well, in this direction, the curve would be concave down if you slice it with the plane here. Not a good thing to do to a saddle or a horse. or the person riding, you know what it is. But you can imagine the plane and the intersection of that plane, okay? It's like this, but in this direction, the plane is like this. You know, the intersection with the plane is an upward parabola, okay? Well, in some direction here and some direction here, that all balances out and everything is flat, okay? There's a point right there where the thing really is pretty much flat, okay? So it's an example of how the graph could be concave up this way, concave down this way, but still level in one selected set of directions, okay? So you have to take account of fxy. There's a rule for that I'll tell you in a minute, okay? I'll show you where to find that in the book too. So you have to have some comparison, okay? And actually, well, I'll write it down in a minute.